and this is called double zeta valence orbital. So that's what we wrote. Double zeta valence, in which the number of orbitals becomes 17, the occupied orbitals continue to be 5, and the unoccupied orbitals become 12. Of course, the calculations are getting better and better, because as we know, in the LCO expansion, this goes to the exact limit provided K is very large. Similarly, we can do triple zeta valence, which would mean there will be another sets of valence orbitals in both hydrogen and carbon, and the number turns out to be 25 for the methane. Of course, you have to do the calculations for every different molecule separate. In addition to this, we would like to use polarization, which means we actually add a basis function whose angular momentum is higher than the valence. So for example, for carbon, we use a D function. For hydrogen, we use a P function. Although they are not there in the valence shell, we can still use it because the whole idea is to make K as large as possible, the basis set as large as possible. So if you use such a basis function, then it will become double zeta valence polarization or triple zeta valence polarization. So it depends on what you add this. So if you continue, I'll come to the next, maybe I'll come. And then of course we also talked about diffuse functions and so on. So I will come to today's class and continuing with the basis functions. So let me now take an example of a polarized basis. So double zeta, let's say valence polarization with the same example of a methane. So then you have a carbon, which is valence will be double zeta. So 2s to p and 2s prime to p prime. Prime is just an indication that's another set of s and p orbital. Then we have a D function because now it's a polarization. And if I don't mention anything, then by default, it's just a 1D function. So similarly, then for hydrogen, it will become 1s prime because it is a double zeta valence, and then a polarization function, which will be a P function, 1P function, which is basically 2P. This will be basically 3D. I'm not worried about that, but it's a D function and 1P function. And of course, for the valence, I'm indicating the quantum numbers. Here, I'm not indicating, but it should be obvious. So I will have similar for 1s prime and a P function, 1s prime for a P function, 1s prime for a P function. So you can see the number going up very quickly. So the same calculation which had given 1 plus 4 plus 4, 9 orbitals for carbon will now become, with the addition of D, which is 5 orbitals, will become 14. There are some old programs, which I will not mention here, but there are old programs in which D used to be 6. So the way they used to do a linear combination, it used to actually give 6, but it is, I think most of the modern programs have D as 5, so the number remains 14. In this case, they become 5, 5, 5, 5. So you can see, even with double zeta valence, a polarized basis, one polarization for the methane, the calculation now has 34 basis function. Again, these are special orbitals, which means 68 spin orbitals, because you have to always double with alpha and beta, and then out of which 5 special orbitals are W occupied, 29 orbitals are unoccupied. So you can very quickly see how the basis set can change. Of course, you can do triple zeta valence polarization. So you add 4 more here, 1 more here. I will not go and do this, but you can see 18 and then so another 8 increase. So it will become 42. All right, so you can keep doing this calculation. It is very, very simple. The calculations are extremely simple. In addition, as I said, you can use the diffuse function. So I want to just explain the concept of diffuse functions. So basically, they are used where long-range interactions are very, very important. And basically, the orbitals or the electron has an effect at a very large distance. So these are typically case of an anion, excited states, and many of the intermolecular interactions, weak intermolecular interactions. So in this case, you need to add a function, because basically if you look at the orbitals, so if I look at the 1s orbital, for example, it actually will fall very fast. It's an exponential minus alpha. Of course, you can take 1s square, which will have a different characteristic, almost similar. Then you can multiply by 4 pi r square to have a density, probability density distribution. All that is unimportant. The important thing is the tail, that how quickly the orbitals are becoming zero. That is the point where I'm really reaching infinity. Whereas in the actual case of an anions and excited states, this should be there at a large, much larger distance. So I need a function which will come like this and have a large distance effect. So how do you do that? It means you have to dampen the fall, the exponents. There are exponential functions. You have to dampen the fall of the exponentials. How do you dampen the fall of exponential? So if you have exponential minus zeta r, of course r minus some coordinate, let's say r alpha, then to make sure that this has a long tail, which means at a large r, this should still have some value, you have to make zeta smaller. So if zeta is smaller, then this function will have longer tail. So I hope you understand what I mean by tail. It should actually go here. So all of you understand this. If I have an exponential minus x, so let's say this is e to the minus x versus e to the minus 0.5x. So at x equal to 0, both of them are same value. So it will start here, but 0.5x will go like this. So e to the power minus 0.5x. So as this exponent decreases, this will have a long tail. As the exponent increases, it will move much faster. So that's the meaning of this coefficient. The exponential function decreases very fast. Exponential negative function decreases very fast. But then how quickly it decreases depends on the coefficient that you multiply. So if you multiply a very small quantity, zeta, then you are typically done with this diffuse function. So you have to add an extra diffuse function, because the valence orbitals that we normally add do not have that small a tail. They're the typical 1s, 2s, 2p function. I want diffuse functions which should die much slower than the valence. So typically, diffuse functions should have much lower zeta values. Sometimes they call exponent zeta values compared to the valence orbital, the normal valence orbital, valence. So we need to add these separately. I can't simply change the valence orbitals, because if I change the valence orbitals, then the valence orbitals effect will go. So the diffuse functions typically are done with a much smaller value, and I will come to the value later, but then typically I would say between 0.01 to maybe 0.1 at the most. So the zeta values are very, very small. All right. So with that, we can tune various different basis functions as we want. As we want, we can tune the basis functions in this. So these are some of the typical basis functions which I discussed. However, there is a very important part of the basis functions that I mentioned yesterday, and that is basically completes the basis set literature. This, I said that whatever we are discussing so far are atomic orbitals, which are basically called the Slater orbital, whose radial part, of course, there's an angular part. Radial part has an exponential form, which is exponential minus zeta r minus the coordinate of the atom. So this is a typical part that happens in the. Of course, there are other things, but the exponential form really appears like this. in all of the Hartree-Fock and density functional theory calculation, either you do Hartree-Fock, ab initio, whatever, we encounter certain integrals which are called the two electron integrals. I think just to understand this part, we have to get into this. The two electron integrals, when I calculate the Hamiltonian matrix element, or even in DFT, I have now orbitals. Remember, Kohn-Sham DFT has spin orbitals, right? So when I write this in terms of the orbitals, I encounter what are called two electron integrals, which in terms of basis look like this. So a atomic orbital a nu, 1 by modulus R1 minus R2, sum a lambda, a sigma. So these are the two electron integrals where electron coordinate here, let's say 1 with a complex conjugate, coordinate 2 with a complex conjugate, here it's 1 and 2, and then the Dirac notation suggests that you integrate over dqr1, dqr. These are called the complete two electron integral. There are some numbers. Since these are all basis functions, like for example methane, it is possible that one of these bases is centered on one carbon. This is basis on a hydrogen 1. This is on a hydrogen 2. This is on a hydrogen 3. So if you look at this integral, this is the most complex integral because although it's a two electron integral, they are based on 4 different atoms. It can happen, simplification can also happen, where all of them can be on the same atom, or 2 of them can be in the same atom. What is the complexity if they are on different atoms? If you look at this later, it multiplies by an R alpha for that particular atom. So the form of the exponents will actually become different because of this R alpha, which will be different for each of the atoms. These kind of integrals are called 4-center two electron integrals. I think it is very easy to understand what it is. There are 2 coordinates, 1 and 2, which are being integrated. So it is called two electron integrals. And there are 4 atomic orbitals, which can be at the most based on 4-center two electron integrals. It so turns out that in the Slater, if you use Slater orbitals, or Slater type orbitals, which are often called STOs, such integrals are very cumbersome. To calculate. If you notice, electron 1 is sitting on this atomic orbital and this atomic orbital. Provided I can multiply these two, a mu and a lambda, and if I could make one Slater orbital, then this would have become 2-center, 2-electron orbital integral. But that is not possible for Slater, simply because a product of 2 Slaters, so this is often called STO. So let me write this. Product of 2 STOs based on 2 atomic centers is not a STO. So I don't get a Slater orbital if I multiply 2 Slater orbitals. This is the mathematics. I will not qualify anything more. And this makes it complicated to reduce the 4-center to any lower number of centers. On the other hand, mathematically it is known that if I take product of 2 Gaussian orbitals based on 2 centers, then the product is also a Gaussian. Of course, it will have a center based on some center. That can be calculated. It will not be on any of these 2 atomic orbital center, but somewhere in between. But then what will happen? I can combine these 2 for one Gaussian. I can combine the a nu and a sigma on which electron coordinate 2 is there in one center. And I can reduce this 4-center to a 2-center integral. So Gaussian has that property. What is the difference between Slater and the Gaussian? The main difference is in the radial part, where the exponential part now becomes exponential minus alpha or minus whatever our atomic center square. So if you look at the Slater and the Gaussian, you have an exponent r minus r alpha. Here also you have an exponent. I can call it zeta, I can call it alpha. Since I'm using alpha, I did not use alpha here, I call it RA. But the important difference is that this is square. So basically, if this was an origin, the Slater and the Gaussian differs in this manner, in a very simple manner. If this is origin, this is exponent is 1, then very simply, this is Slater, this is Gaussian. So I hope you can understand. So it's basically exponential minus x to exponential minus x square. Now, it makes a lot of difference. It makes a huge difference because this is an even function of r. Okay, this is not an even function of r. So, and this is, remember, this is vector. So it has x, y, z component. So if I write Cartesian, this will become exponential minus x and exponential minus x square. They have a completely different character. So the exponential minus x, if you do the calculation, this will be from here, starting from here, it will go like this. And of course, here, it will actually keep on increasing. Whereas in minus x square, so this is e to the minus x. Whereas if you look at e to the minus x square, it is even. It will actually go down to 0 on both sides. It will go up and then go down again. So this is very symmetric curve around x equal to 0, where it has a maximum value. And very often when you look at our score evaluation, we always discuss how many people got A, B, C, D, etc. We always say the ideal curve is a Gaussian curve because of this, the kind of function that we have, that somewhere there is a peak and it goes. This is not an ideal curve. Okay. So I'm trying to say that when you write in terms of the Cartesian Gaussian, x, y, z, the Gaussian has this square, and because of this, Gaussian has this property. Now, I am not going to do the mathematics. Why? But the square itself changes the fact that the product of two Gaussians is a Gaussian, whereas in the Slater, where the square is not there, the product of two Slater is not a Slater. And hence, reduction of a centers in a multi-center 2-electron integrals is possible. If I use Gaussian orbitals. By the same definition, I can call it GTO. That is STO, this is GTO. So how do I use Gaussian orbital? Now that's it's good to know this mathematics, but if you go back to my atomic orbital basis state, what did I do? I did a molecular orbital. If you go back to the last class, I summed over the basis. Of course, I can use any basis. I have deliberately written the coefficient such that the column will indicate one molecular orbital. All right. So I already told you that the chemists are intuitive. So the chemists wanted to use these as atomic orbitals. Of course, I can use anything. I can use Gaussian. But then I initially said that I want to use atomic orbitals because I want to do the molecular calculations fast. And now I know that the atomic orbitals are Slater. Atomic orbitals are not Gaussian. They are Slater. But then I come to a situation where integrals, which are 2-electron integrals, are very hard to calculate. So then I start to think, what do I do? So the way to think was that, can I represent, and this is the thought that has really made computational chemistry extremely doable. Can I represent one Slater orbiter in terms of a few Gaussian of that particular, centered on that particular atom? So Gaussian will exactly have the same structure as I told you, R minus Ra, which is the atomic center, and some alpha square of that. So whatever is the Slater center, can I write this in terms of a combination of Gaussian at least? So what I want to do is that one STO, can I write as a linear combination of some alpha equal to 1 to d, some d number of Gaussian, which is basically the coefficient, or let's say p number of Gaussians, coefficients d alpha, exponential minus some exponent alpha times r minus Ra square. So I'm summing over this, and these are the coefficients d alpha. So basically I'm taking a linear combination of one Slater orbital in terms of the p number of Gaussian orbitals. That may be possible. That is because, again, mathematics tells me one atomic function can be written in terms of a complete set of functions. But then again, there is a separate kind of error that coming in. The same completeness that I had encountered here will also now come and encountered here. So that's the second level of error in the basis set. So one is, of course, number of k that I'm introducing. Then the second level says each of these Slater orbitals, how many Gaussians you are expanding. So that's my second level of problem. How many Gaussians am I expanding for each STOs? So there are two kinds of basis set problems that I'm bringing in. One is, first of all, how many atomic orbitals I'm using. And I already discussed double zeta valence, triple zeta valence, polarization, etc. And each of those functions, I don't want to write in Slater. I want to write in terms of Gaussian. So this becomes an additional level of problem, but people have solved it by independently solving atoms without bringing in molecule. They have fitted the STO atomic orbitals to the Gaussian. This is a fitting that is done, and this is actually done even before the Hartree-Fock molecule is done. This is already known. So this fitting is already done independent of the Hartree-Fock. So the Hartree-Fock we don't bring in. We simply know this combination and then directly go to the two-electron integral, where each of these orbitals will now be expanded in terms of these Gaussians. Okay, so that is in terms of this Gaussian, sorry. In terms of, in terms of these Gaussians. So each of the mu, this is going to be one of the mu orbitals, which is expanded in terms of this Gaussian. So I already know the fitting, I already know the d alpha, I already know this zeta alpha, everything, Gaussian. So these zetas are different from the zetas that I talked about. So let me expand this, let me explain this with the primitive basis, the minimal basis. If you go back to minimal basis, how many STOs I had? So I again going to take the example of methane, my favorite molecule, and look at the carbon as 1s, 2s, 2p. This is a minimal basis, remember. So I don't have double zeta, triple zeta. So I have only 1s, 2s, 2p. For hydrogen, I have 1s, 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 1s. This is what I started with. These are the 9 orbitals. But these were all Slater orbitals. These are all STOs. What I'm now going to do is to expand these STOs in terms of a known set of Gaussian. I already know this. So this will be the first level of minimal basis sets, and the minimum number of Gaussian. So here also there is a minimum. So minimum value of P which is the minimum number of Gaussian required to expand any of the Slater orbital, is taken to be 3. Otherwise, you get a very bad representation of each of them. So if each of the Slater orbitals is expanded by 3 Gaussians, this basis set is now known as a minimal basis, but it is simply written as STO3G. So now I'm going to give a new nomenclature of all the nomenclature that I give, which will include the number of Gaussians and the number of Slater orbitals. So when I write in general STO3G, it is known to be a minimal basis with each basis expanded in terms of 3 Gaussian. Now these are all nomenclature. So please understand, we have a convenient acronyms for each basis. The number of atomic orbitals is still the same. Remember, number of atomic orbitals is still 9. So nothing will change. Number of occupied orbitals 5, unoccupied orbital 4. The number of molecular orbitals will depend not on this, how many you use Gaussians, but that will depend on the scale. That will not change. Each of them, for convenience of computation, has been expanded. But the actual number that the phi will generate, the actual number of molecular orbital that will be generated will of course depend on the scale. So none of that will change, number of actual basis functions. But each of the basis function has been expanded in terms of 3 Gaussians, and this minimal basis is now called STO3G. Very similarly, I can expand in terms of 4 Gaussians. This is the minimum. So I have STO4G, STO5G, and so on. I hope, because I am not changing the number of atomic orbitals. I am only changing the description of each atomic orbitals by introducing a large number of p, from 3 to 4 to 5 to 6. But each of these belong to the minimal basis. So if there is a calculation where I say I did Kohn-Sham DFT or Hartree-Fock with a minimal basis, or simply they write STO3G, you understand what it is. So there are 2 things you understand. I don't write minimal basis. This is minimal basis. So 2 things is that if it is for methane, I know I have 9 molecular orbitals. From here, I know this is minimal basis, 9 atomic or molecular orbitals, and each 9 molecular orbitals out of 9 atomic orbitals, which are STO, and each AO is expanded in 3 Gaussians. So, but remember, when this expansion, when I'm talking, this is only to give a good quality atomic orbital. It really does not tell, it does not change the number of basis functions. Okay? Because that is determined, I'm again repeating, that is determined by the number of atomic orbitals, number of Slater orbitals, not by the number of Gaussians that are used to expand atomic orbitals. So STO3G has a 9 MOs. If I do the same calculation with STO4G, how many MOs will be there? Again 9. Because STO4G just expands each AO in terms of 4 Gaussians, but the number of AOs continue to remain the same. So number of molecular orbitals that you will get is just 9, except that each atomic orbital, hence molecular orbital, will be little bit better described. And the energy in STO4G will be slightly less than the energy in STO3G because of a principle, what is called variation principle. The more the merrier. It is not here more number of K, but it is because more number of P, the atomic orbitals will be a little bit better described and the energy will always go down. So that's the variation method. Energy will go down if you use larger and larger basis functions. So you will get a slight improvement in energy. But other than that, the qualitatively you will get 9 MOs, 5 of them occupied, 4 of them unoccupied. We now go to the next basis set, which are the double zeta valence, triple zeta valence. Very often, those are called split valence bases. And I just wanted to introduce this term, the split valence. I hope you immediately understand why the split valence. So let's say DZV, I had already written. For carbon, you have 1s, 2s, 2p. Sorry, 2s prime, 2p, 2p prime. So it is split valence because I'm splitting the valence into two. One set of sp, another set of sp, which I'm calling s prime, p prime, and so on. I can have a triple zeta, so splitting, I can have a more larger number of splitting. Yeah, I'm sorry. So now the Gaussian. So for each of them, each of the carbon atoms have to expand in a Gaussian. I will come to hydrogen a little later, but hydrogen has, of course, 1s, 1s prime, and so on. 1s, 1s prime, 4 of them. I have to expand each of these now. Now that I know, I can't work with Slater orbital, but the number of molecular orbitals is fixed. I've already told you what is the number. There will be 9 here and 2, 8 here, so 17. So that number is fixed in double zero valence. But I have to now use Gaussians for each of them. So one standard Gaussian that is used is for the core orbitals, like 1s here. For the carbon 1s, you use 3 Gaussian, just like you did for the STO3G, where everything was expanded in 3 Gaussian. Here, the core orbital is expanded in terms of 3 Gaussians. The first set of valence orbitals, which is 2s, 2p, each of them are treated in the same manner, s and p, is expanded in terms of 2 Gaussians. And the second set, 2s prime, 2p prime, is expanded in terms of only 1 Gaussian. This is one example, but you can use more and more. As I told you, you can use more and more. More number of Gaussians will not change the number of atomic orbitals. I'm again repeating. They are determined by this. They will only change the quality of the atomic orbitals. But let's assume that I did for the carbon 1s 3 Gaussians, the one set of valence orbitals 2 Gaussians, another 1 Gaussian, and the same thing I do for hydrogen. So for hydrogen, of course, both of them are valence. So 1s I use 2 Gaussians, 1s prime I use 1 Gaussian. And I do the same thing for all the 4 hydrogens. I'm not going to write. This particular basis set will be nicely nomenclatured in a way that everything, that it is double zeta valence plus the number of Gaussians, everything will be recorded in one nomenclature. And the nomenclature is 3-21G. It's very often called 321G. You will now realize why. This dash separates the core and the valence. The number of entries. So let me first say the separator, dash is a separator. Between core and valence. The left of the separator is core. The right of the separator is valence. The number of entries, not the actual value, number of entries determine the number of core or valence orbitals. I'm only discussing the valence right now. I'm not discussing polarization, diffuse function. We'll see how to do that. So this is the number of entries. So for example, what is the number of entries to the left of this separator? 1, not 3. It is not the number. It is the total number of entries which are there to the left. It's only 1. And to the right, it is 2. This means in terms of atomic orbitals, 1 core and 2 valence orbitals are given. So that is basically, it immediately tells me that is double zeta valence, whatever I have done before, because number of entries here are 2. Then you will ask the question, what does these values mean? They will now tell you that the core, which is only 1, is expanded in terms of 3 Gaussians. First set of valence is expanded in terms of 2 Gaussians. The second set of valence is expanded in terms of 1 Gaussian. But the number of atomic orbitals, I repeat, the number of atomic orbitals have nothing to do with this 3, 2, 1. They are only determined in this nomenclature by number of core orbitals and number of valence orbitals. I hope it is clear. So for this methane calculation, the total number of AOs is 17 in DZVP in 321G, because this is identical to the DZVP, because I have 2 entries, which means I have a situation where carbon is 1s, 2s, 2p, 2s prime, 2p prime, hydrogen 1s, 1s prime, 1s. So this is 9 plus 2 plus 2 plus 2 plus 2. That's 17. But these numbers do not contribute to the 17. What contributes to 17 is the number of entries. From the number of entries, you can make out. So I'm going very slow deliberately because I think many people, unfortunately, make a lot of mistakes in basis sets. So I'm going very, very slow. If I can't finish functional, I will request all of you to come back for one more day, because I'm looking at the watch. I'm not very sure that I'll be able to. I hope, Subhajit, that is okay. One day, 1 hour is okay.
Perfectly okay.
If I can't finish, but I don't want to rush to finish it today. Okay. Let me see where I go. All right. So I'm repeating once again, the 321G and DZV, DZVP. Sorry, DZV is identical because it also gives you 17 orbitals. It's not polarization, so I removed. I'm sorry about it. But these values 3, 2, 1 have no meaning. They have a meaning only in terms of improving the quality of atom. How many Gaussians are there in each atom? But number of atomic orbitals is fixed, and hence number of molecular orbital is also fixed. That's also 17. But this tells me how many Gaussians are there for one core. And first set of valence, this is a set. First set of valence, which is SP, and second set of valence, S prime, P prime. When you come to hydrogen, I have only valence. The first set is 2, second set is 1. That's all. What do you mean by 1 Gaussian? 1 Gaussian means I'm actually not taking linear contribution. So very often, a Slater orbital with 1 Gaussian has a name that is called uncontracted Gaussian or uncontracted Slater orbital, whatever, uncontracted Gaussian. It means I have a Gaussian which I'm not contracting. Contraction is basically linear combination. So normally STOs will be called contracted Gaussian. So this is also another name that I want to introduce. STO, which is Slater orbital, is also called CGTO, contracted Gaussian type orbitals. And the actual Gaussian orbitals before contractions are called primitive Gaussian orbitals, PGTO. So from the primitive orbitals, I contract them to get a CGTO, which is Slater orbital, and then I get molecular orbitals. So I have a PGTOs, mix all of them, some of them, I get CGTO, and then I get MO. So I have just changed the nomenclature. This was my originally what I call Gaussian. This is Slater. This is the MO. This number and this number is identical. Primitive Gaussian number can be anything because some number is making up this contracted Gaussian. But this is very important. This is my K. This is my K number, the basis set number. So there are different nomenclatures, so I want to introduce that. But let me now come to another basis. I'll simply write it now. So let's say I write 431G. You might have seen this basis. You should be able to tell me now. for the methane, how many basis functions will be there? What is the value of the K? If I quickly see, the number of K is identical in 321G and 431G, because right of separator, the number of entries is 2, still 2, and number of entry to the left is still 1, which means I have one set of core, I have two sets of valence, 2s to p, 2s prime to p prime. The difference is that the core was expanded in terms of 3 Gaussians here, and the valence was expanded in terms of one set with 2 and 1. That has changed to 4 for the core. First set of valence with 3 Gaussians, second set of valence is 2s prime, 1 Gaussian, uncontracted. That is all that has changed, but the number of MOs is still 17. Nothing will change. The quality will change because it is a higher number of Gaussians. The energy, of course, in 431G and 321G will not be identical. I'm again repeating, the energy will be slightly lower here because I've used more number of Gaussians to explain the CGTUs, to contract, to form the CGTUs or Slater orbitals. I can have 631G. Now the very famous basis set which you are always using. Nothing changes. It's still 17. Because the number of entries are still 2 and 1. Nothing changes. The quality of atomic orbitals changes. It is 6 Gaussians, 3 Gaussians in the first, and 1 Gaussian. So this part is same. In fact, 431G and 631G are almost same, except the core is little better represented. Core has 6 Gaussian. So the atomic
orbitals. Why do we put so much of stress on the core? I mean, why?
Yeah, that's a good question. That's a good question. So you can actually live with 431G. In fact, if you do a calculation of 431G and 631G, you will actually realize the difference. The difference will be minor. I am still taking only one core function in both the basis set. I am just saying that the core orbital I am representing somewhat better by taking number of Gaussians, more number of Gaussians. So this is where I am just saying that the core orbital I want to represent better. So the core orbitals which are actually bound, they need to be really atomic in character because they are very close to the nucleus. To have that atomic in the character, if you have noticed, every basis set, I don't know if you have noticed this, core always has more number of Gaussians than the valence, because of the fact that the core is more atomic. And it's a very loose statement than valence. So I need core to be represented more like atomic orbital, STOs. And I know that STOs are different from Gaussians, so I need more Gaussians here rather than in the valence. And you can see the second valence here, I'm getting away with only 1. You don't need really one. One good valence, which also has a less number of Gaussian, but the core is very tight, and I don't need too many number of core. But if you're using core, I must use a good core orbital. Now, that is the reason. The idea is always to use a balanced basis set. So when I use 321G, I did exactly the same thing. I used I used 3 Gaussians for the core, and then 2 and 1 for the valence. So it's important to always represent the core. So what we normally think that core is not important, here it's a different point that I'm saying. It is important to represent the core. So core requires more number of Gaussian. So more number of PGTOs, primitive Gaussians, than the valence. But number of core orbitals, I don't require many. So when I'm expanding molecular orbital, then the number of core orbitals can be 1, but whatever I use, they require more number of Gaussians because they have more atomic character. Is it clear?
Yes, thank you.
So of course you can say that what is the difference between 431G and 631G? Yeah, the difference is going to be very, very minor. I agree, but I mean, you can just do a better job. These kind of basis sets that I'm using were first designed by Pople, the split valence basis set, and very often they call Pople basis sets. is a Pople nomenclature is given by Pople. The earlier nomenclature, when I did not introduce the Gaussian concept of Gaussian, and where I simply said DZ, VP, and so on. Yeah, I mean, I don't know if I'm there. It was there in the last class. So basically, the earlier nomenclature did not have a primitive Gaussians, but it had only the concept of like DZ, VP, and so on. DZ, VP, TZ, VP, triple zero valence. These were called the Dunning basis set. It's just to tell you the history. There is a person called Dunning, Tom Dunning, who actually developed this basis set, and they used the Gaussians which are developed by Fujinaga. So this kind of basis sets using Gaussians are very often known as Fujinaga-Dunning basis in the literature. But then when Pople came, he changed the nomenclature. He changed also the number of basis function, exponent, everything, and they are now called in the way 61G and so on. So these are Pople nomenclature, and they are often called Pople basis set. Let me now say, how do I explain TZV in Pople nomenclature? So one of the basis, of course, number of Gaussian is not an issue. I can use any number of Gaussian, but if I use same 61G, then if I write 6311G, you can immediately see this is triple zeta valence. I hope that is clear now, because from the separator to the left, I still have one core, but now I have three valence, 2s to p, 2s prime to p prime, 2s double prime to p double. Note again, the core is, when I expand in terms of Gaussians, I require more core. For the valence, one expansion is good. The other two I can leave uncontracted. But this is a TZV basis set, triple zeta valence basis set. And I can continue to write like this. This is a standard basis set. Of course, you can use more number here. So you can even use 10, 4, 2, 1, G. I'm just making up a basis set. No problem. This is still triple zeta valence. It's just that every orbital is now better described. I hope you can understand. This is now 10 Gaussian. The first set is 4 Gaussian. Second valence is 2 Gaussian. Third, I leave uncontracted. And the result will be slightly better than this because of the atomic orbital quality, the Gaussian will go down, but number of atomic orbitals will be the same. So I already told you what will be the number in TZV. That's a 25, right? TZV was 17. So if you do 10, 4 to 1G, it is still 25. So if I just ask you a question, what are the number of molecular orbitals? So I ask you a simple question. What is the number of molecular orbitals that will be generated for a methane calculation in 10-421G? Many people will get totally confused. The answer is still 25, because this is a triple zeta valence quality. And triple zeta valence quality means 1s, 2s, 2p, 2s prime, 2p prime, 2s double prime, 2p double prime for carbon. And then for hydrogen, 3 functions. So this is already, you can see, 4, 4, 4, 13. So 13 and 13 function. And then you have a hydrogen, which is 3 functions. So 3 plus 3 plus 3, I think it's 22 functions. Yeah, no, there are 4 hydrogens, right? So that's 25. So 4 hydrogens have 3, 4 into 3, 12 plus 13, 25. So that's the number that I talked of yesterday. But if I do 6111G, if I do 10-421G, number of molecular orbitals is identical. Because that is important. At the end of the Kohn-Sham calculation, number of molecular orbitals is identical, because I can ask you a question, how many unoccupied orbitals you get? Occupied is also same for methane. This is the most important number. This is going to keep changing. So for any of the TZV calculation, this number will be 20 for methane. I hope all of you are understanding what I'm saying. Is very simple. This number game is very simple, but people get fooled by these numbers and unnecessarily start to compute 10, 4, 2. That is only for the quality of the atomic orbitals. But the number of atomic orbitals are determined by the number of entries to the right of the separator and the left of the separator. All right. Let me come to now Popel's nomenclature of polarized function. So let's say DZVP, double zeta valence polarization. How am I going to write? I can take several double zeta functions in Popel's basis. So let's say I take 631G. And then I want to add a polarization to carbon and a hydrogen. So the way Popel did initially is to write this with a star. The star means in addition to the 631G basis, which is basically double zeta valence quality, because there are two entries here, I've added a polarized function. Now, in addition of the polarization function, initially, see that's the problem of basis literature, that there are too many literature, as you can see. Initially, they distinguished between the carbon polarization and the hydrogen polarization. Then they said, if I use only star, it means the heavy atom. Of course, heavy atom is a wrong nomenclature. Heavy atom means first row atom. The first row atom has polarization, not the hydrogen. If I use double star, then the hydrogen also has polarization. So I hope it is clear. When we did DZVP, we did not distinguish between carbon and hydrogen. We add polarization. What is polarization? For carbon, that is D. For hydrogen, that is P. So I have a kind of nomenclature which says I have used the basis functions with polarization. So if I write 321G star star, it will mean exactly the same. What is the number of basis function? That's same as DZVP, because the double zeta valence polarization is added. So I should be able to calculate the 321G star star or 631G star star, identical, except that the functions are a little better. So what will be the number for the methane? Do the calculation for the methane once more. I'll do this tutorial. So carbon has still 1s, 2s, 2p, 2s prime, 2p prime, because it's a double zeta valence. And hydrogen will have 1s, 1s prime. But carbon also will have a D function. It's a 3D or whatever. And hydrogen will have a P function, because it's a polarized function. So this number with a 5D function now becomes 4 plus 4 plus 1, 9 plus 5, 14. I've already done this calculation. I'm repeating it. These numbers now become 5, 5, 5, 5, and the number in either case is 34. So number of molecular orbitals is 34. Either I do 321G star star or 631G star star. The question that you will ask, what is the number of Gaussians for the polarization function? And very often, all these polarization functions, this is standard nomenclature, all these polarization functions are just one Gaussian. So basically uncontracted Gaussian. They have, of course, the exponent. Gaussian means I have to define the exponent. Uncontracted Gaussians on that particular atom. The center is carbon, so some values are there. Those are all given. So there are tables of all the exponents, the zeta values. But basically it means uncontracted one Gaussian, all the polarized. So it's very simple. And 6,3, so I don't need to do anything to indicate number of Gaussian. Number of Gaussians will only come here with 6, 3, and 1. Number of valence orbitals, number of core orbitals are given by the number of entries. I again repeat, number of entries, not what is there in each entry. So that's a standard way of writing. And if you give only heavy atom, write only star. Then comes the diffuse functions. Again, diffuse functions can be given as a set of functions on carbon and hydrogen. And diffuse functions are usually valence functions. I told you, with a very low exponent. Because what is the idea of the diffuse function I explained today? That they must die very slowly. So they are very, very low exponent and they are again uncontracted. So one Gaussian. So hydrogen also has a valence function. Valence is of course S. So here I have a SP, I have S here. So the diffuse functions are written in the Popel's basis in the following manner. 3, 2, 1 G. So let's say I have done diffuse for both carbon and hydrogen. Then I write 3, 2, 1 G. 3, 2, 1, sorry. 3, 2, yeah, this is written slightly differently. Plus, plus, then G, then star, star. Now, what will this mean? This plus plus indicate diffuse function again for the heavy atom or first row atom and hydrogen. Star star indicates polarization. 2 1 indicates that it's a double zeta valence. So you have a DZ VP with diffuse functions on both carbon and hydrogen. So what is the total number of basis functions? Please let's try to do this again for the methane. So how many carbon atoms are there now? 1s, 2s, 2p, 2s prime, 2p prime. That's the first thing. That is this with 3 here, 2 sets here, 2 Gaussian here, 1 Gaussian here. But now I have a polarization function. So there's a D function. Call it 3D or whatever. Then I have an additional SP. So they are now diffuse function, not the valence one, not like triple zeta, but a diffuse SP. So I have a diffuse S and P function. I just keep it like this. So what is your total number? They are not really like a valence orbital. So it is not triple zeta valence. Don't confuse it this. But they are S and P function, but they're very low exponent. So they can't be valence. But what is the total number of carbon bases now? 1 plus 4 plus 4, 9 plus 5, 14 plus another 4. So this is 18. For the hydrogen, I have again double zeta valence. The 3 is not important here. So it is 1s, 1s prime because hydrogen doesn't have a core. So 1s, 1s prime, and then a 2p function, which is basically, or a p function. 2 is not important, 3 is not important, a p function. And then one set of diffuse function on the valence, which is just S. So what is the number here? 1 plus 1 plus 3, that's the DZPP, 5. Plus 1 more, so 6. So now what's the total number of atomic orbitals? 18 plus 4 into 6. There are 4 hydrogens. So for methane, it is 18 plus 4 into 6, 24, which is 42. It's a diffuse, it's a DZVP with diffuse function. Remember, I also did a calculation with TZVP. Yes, yes. Any question? Can you, if there are no questions, can you mute it? Yeah. You remember I did a calculation for TZVP, which is also 42. Because this is like TZVP. I have a diffuse function. If I add this as a valence function, then the number will be exactly like TZVP. So TZVP and DZVP with diffuse function actually lead to identical number of atomic orbitals or identical number of molecular orbitals. The K value is identical because when I do the number counting, it doesn't matter whether it is diffuse or not diffuse. You understand? It is S and P. So either I'm doing TZPP or DZPP with diffuse. Of course, if I do TZPP with diffuse, that number will be more. So I will be able to calculate once again. It's very, very simple calculation. Just keep your head. It's very easy. So I can write a diffuse function as also 631 plus plus G star star in a Popel nomenclature. It's just that same 42, the valence instead of making 321G is now 631. So the number of atomic orbitals have not changed. I hope it's clear. If there's any question, please ask me.
Sir, please repeat the diffuse function part.
I think I already told you the diffuse functions in the very beginning of the class. Maybe you didn't join. Who are you speaking? Hello? Hello?
Porna.
Okay, Parna. Yeah, I thought so. So maybe you didn't join in the beginning. See, when you do calculations for the anions or excited states or
Yes, I have
Or-
joined. That I understand.
yeah,
The
long range
calculation.
interaction, you need the functions which are very low exponent. These are typically SP functions. So the number of orbitals that are added is one set of S orbitals, atomic orbitals, and one set of P orbitals.
Yes, yes.
So this is exactly like a triple zeta valence. In triple zeta valence, compared to double zeta, I'm adding one more S and P function. So I do exactly the same thing here. One more S and P function. The fact that they have low exponent has nothing to do with the number. The fact that they have a low exponent to be characterized as diffuse
Yes,
function has nothing to do with the number. Your number of S and P together is always 4, right? S is 1, P is degenerate 3. So in terms
Yes,
of number
thank you,
count,
sir. Now I
yeah, you understand? Yeah, in terms of number count, DZVP with diffuse is identical as TZVP. So please don't get confused. But it does a completely different job. TZPP has also 42 atomic orbitals, but it is only improving the valence. Where diffuse is required, this will not do the job. So depends on what you require, what you want. If I'm describing an anion, you want to use only 42 orbital. That is what your computer allows. Let's say, hypothetical case. I would rather say use DZVP with diffuse rather than TZVP. I hope you understand, because here you have no diffuse. That is bad.
Yes, sir. No.
Okay. So, so it depends on what you want to do. So we should not jump into conclusion that the number is 42, so both are identical. No, they are not identical. They'll have a completely different level of, because I'm using diffuse here, I'm not using diffuse here. Diffuse does a different job. So, so this is a diffuse and a polarization function, 631 plus G star, or if I can use 631 plus 6311 plus G star star. This is triple zeta valence. Of course, you can see triple zeta polarization with diffuse. Is it clear? In the Poppel's nomenclature, they have later changed it. And I must say, because they were finding this rather uncomfortable to write. Star, star, plus, plus, and so on. More so, because Poppel later realized in the Poppel's group that I can have more number of polarization functions. See, so far I've been talking of polarization, which is only one set. So for carbon, I'm using D, hydrogen, I'm using P, only one set. If I want to use 2D functions, how does this nomenclature will allow me? Because it still has star, star only. So later, Poppel started to do the calculations like this. The 631G diffuse functions are usually only one set. So he continued to use plus plus, but instead of using star star, he started using 2D 1P. Now you understand what it means. So if I say this is my basis, what do you understand now? It's a double zeta valence with diffuse. That's the first thing. So it is like triple zeta valence. But the polarization is for carbon, I have a 2D functions. For hydrogen, I have a 1P functions. Well, 2D means it is not 2D. 2 is not the quantum number. It can be 3D, 4D, doesn't matter. But 2 number of D functions, hydrogen is 1. So this is a little bit modern nomenclature, which allows you to change. The star star was little bit restrictive because it cannot tell how many polarizations. Plus plus is okay, because we normally use one diffuse function. But today people are also using more than one diffuse function. So just the nomenclature will change. I mean, it's not important to know the nomenclature, but what is important is how many basis functions are there. So if I do the calculation, carbon it is exactly like 1s, 2s, 2p, 2s prime, 2p prime, and 1 diffuse sp. So it's like a triple zeta valence, but now I have a 2d functions. So d plus d. For hydrogen, it will be again 1s, 1s prime, and then one more s functions, which is basis plus 1p function. Because I have written 2d, 1p. So hydrogen is same. So I can just multiply. So just calculate the number here again. 13 here, like a triple zeta valence function. 4 plus 4 plus 4 plus 1. 13 plus 2d now. It's not 5. 13 plus 5 plus 5. So that's 23. For each of the hydrogen, it is 3 plus 3, 6 functions. So total number will be 23 plus 6 into 4, 24, 47. So it is exactly like what I did before, but carbon had one extra d function, so 42 became 47. Of course, if I do 6, 3, 1, 1, G plus plus D, 2D, 1P, the number will change. This will become triple zeta plus diffuse. So number will become much larger. So one more 4 functions will be added to the carbon, one more function in the hydrogen. So 4 plus 4, 8 functions will be added. I hope I don't have to keep doing it, right? Once you understand the nomenclature, you can do anything you want. And as I said, in basis set is really our own feeling, how many I want, and you decide. And the only philosophy is more the merrier. So larger the better. Both larger. You use larger number of K, use larger number of Gaussians to include the K to each of the atomic orbitals. But the larger number of Gaussians do not increase the number of K values. So it does not increase the number of molecular orbitals. Number of molecular orbitals are fixed by the number of atomic orbitals. The quality of the atomic orbital only increases. So I hope I have been able to explain to you the Poepel's basis. There is one more very important basis which has come up in the recent years. Again, this is a little bit complicated, not very complicated, but I will just explain this. And those are called the correlation consistent basis set. In many literature, they're using this, and I think it essentially means that I have to take the functional on another class. So before anybody leaves, can we discuss the next class time?
My suggestion would be what we did last week on
Tuesday.
That would be my suggestion. So if someone has a problem, they can let us.
Yeah, Tuesday 8 o'clock is okay to all. Well, I will now finish the basis. I'll just do the functional. Yeah. Is that okay? So we'll take the Tuesday. So please tell Oshini or Suman to generate the link. Or the link works, that's fine. Okay? All right.
I am available on Tuesday at 8 p.m.
You have problem?
No, I'm there. I'll be there.
Okay, fine. So we have to generate the link.
Yeah.
The link may not have been generated for Tuesday.
Yeah, I
We
will
have
do
to
it.
sample. Yeah, okay. So this correlation consistent basis set were first generated for very good post-Hartree-Fock or correlated calculation in ab initio method, which is called post-Hartree-Fock. And many people are also using this for DFT. So the way these are done is the following. So for example, I will give an explanation. The correlation consistent first comes with small c, cc. Then you write PVDZ. Before I go into a general idea of what it is, I will try to give an example. So let's say I'm doing correlation consistent PVDZ for the same methane. So how many basis functions are included for carbon and hydrogen? I will not worry in this case number of Gaussians, because that is actually part of this basis set. The numbers are all given. It's not important. I'm just quickly giving you the number of atomic orbitals and how good they are. So if you do CCPVDZ, remember this is actually double zeta. Valence is double zeta, but it means this is correlation consistent, and they are sometimes called the polarization. These are called the polarized function. So it stands correlation consistent polarized. So polarization is also included. So this automatically tells you CCBVDZ will be for hydrogen, the 1s prime, that's a 2s functions, and 1p function. So this is exactly like a DZVP for hydrogen. For carbon, or in fact, for the entire group from lithium to neon is the same. So whatever I'm discussing for carbon, incidentally, is same for lithium to neon, that entire first row atom. When I go to second row atom, and that is something that I wanted to mention, like transition metal and all that, the numbers will increase because valence orbitals are much more. So everything will increase accordingly. Okay, so please do not worry about that. I am explaining with the first row atoms and hydrogen because that's more for organic molecules. That is what you require. So for the carbon, it will have a 1s, 2s, 2p, 2s prime, 2p prime. So it's exactly 3 s functions and 2 p functions and 1 d functions. So this is exactly DZVP, polarization function. Of course, if you go for sodium to argon, number of s and p and d functions will increase. Number of sp will increase here because there is a 3s, 3p and so on. I'm not going to write that. Okay. Let me come to CCPVTZ, how things change. Now I have a valence triple zeta. So let me write the same thing for the hydrogen. This is very easy. This is like exactly what we did, DZVP. So I'm not going to write the number. So for hydrogen now, I have, this is CCPVTZ. I have 1s prime, 1s double prime, because valence is triple zeta. So I have 3s function. But very interestingly now, it is not 1p. If I use 3 valence functions, I will actually use 2 sets of angular momentum in the following number: 2p function, 1d function. I'm only writing the atomic orbital. I'm not writing how they are expanded in terms of Gaussian. They can be very similar, like 631G here and so on. This can be uncontracted. All the polarization functions can be uncontracted. But very interestingly, how quickly the polarization build. It is not just 1p or not just a p and a d function. 2p function, 1d function. This is called the correlation consistent. Because I have put triple zeta valence, I have to add the polarization function in the similar manner. Whereas in the normal Poppel's basis set of DZVP and TZVP, the number of polarization functions are always 1. It did not change because the valence has triple zeta. But here I'm changing because the valence is triple zeta. I'm changing the number of polarization. So for example, for carbon, which is now 1s, 2s, 2p, 2s prime, 2p prime, 2s double prime, 2p double prime. That's a triple zeta, of course. And then I have the, so this is basically 4s function and 3p function. But now I have the 2d function exactly in the same manner, 1f function. I hope you understand the scenario. Because it's a triple zeta, I have to use 2 sets of angular momentum, not 1. And the first will come 2 in number, the second will come 1 in number. Just please understand the logic. Don't try to calculate everything because that's will be very difficult. Of course, for carbon, I will have 30 functions. You can calculate that. It's a 4 s functions, 3p functions, 2d functions, 1f function. That's how you should see. So that's the number will be 30. If you go to CCPVQZ, and I think we can stop here for the explanation. So hydrogen has 4 functions. So 1s prime, 1s double prime, 1s triple prime. So 4 valence function. So of course, the polarization will now build up very, very quickly. You will have 3 polarization functions, just 1 less. And they will go like this: 3p, 2d, 1f. I hope you understand how quickly I'm building. Even for hydrogen, I'm now using f functions. Can you imagine? It's a polarization which is now PDF, and numbers cannot be same. The first one is 3, second one is D, 2, third one is F. So the way to build is that the last one you put 1, then 1 addition, 1 addition. It's very easy. And this number itself for hydrogen will become 30 functions. It's so much, so larger. And of course, if I do for carbon, for the CCPVQ, I will have 1s, 2s, 2p, and 4 such sets, 2s prime, 2p prime, 2s double prime, 2p double prime, 2s triple prime, 2p triple prime. And then now tell me, what will be the number of polarization function for the carbon? CCPVQs, I have 5s, 4p. I will have D, F, G, right? I had only DF, but I'll have a, this is a quadruple zeta. So I will have DFG. So it will have 3D, 2F, 1G. I hope it's clear. All of you understand what I'm doing now. So depending on the number of valence orbitals, they keep on increasing. That's the main difference in the correlation consistent basis. The number of polarization add very, very quickly, depending on the number of valence N. So if I have a CCPVNZ, then I have N sets of valence orbital. That is no problem. And of course, N sets of valence, and of course, one set of core. Core is not changing at all. But then in addition to this, I will have N-1 sets of angular momentum. Polarization function higher than the valence. N-1. So for double zeta, only 1. For triple zeta, I'll have 2 sets. Quadruple zeta, I'll have 3 sets, and so on. And their number will be go as this: N-1, N-2, up to 1. So you can see for 4, N-1 is 3, N-2 is 2, N-1 is 1. I hope the mathematics is very clear. And those are all going to be higher than. So I think I don't need to do more in the CCPVQZ and so on. Okay, so basically in the correlation consistent, many of you are using CCPVQZ, CCPVDZ, they're all there. Please understand they're different from DZVP in the sense that in DZVP triple zeta valence polarization, number of polarization function is always 1. Okay, of course in Popple's basis like this, I can use different number. So if I use 6G, 1G, 2D, 1P, that is basically in a way your CCPV triple zeta. For carbon, I have 2D, 1F, right? So I have carbon for 2D, 1F. So I can do a nomenclature in Popple's basis as well. But today correlation consistent is a good nomenclature. So they are very different. Now you will ask me the question, what about the diffuse functions? How the plus? They have not come here yet. Yes, of course they have not come here. That's because I can give a nomenclature. I have not given you a nomenclature, but indeed I can add to each of these diffuse functions. So another SP for carbon, another S for hydrogen. Remember, diffuse functions are only to the valence orbitals. So another SP for carbon, so it will just add up the number. But how will I do the nomenclature? They are called augmented. AUG-CC-PV-NZ. I hope it's clear. When N is doubles, triples, quadruples, etc. I hope all of you will now be able to understand. So if I just say augmented, let me again give you augmented CCPV-DZ. That's easy. I have done this already. Because CCPV-DZ is like DZV plus diffuse function. So this is very easy. Let me come with augmented CCPV-TZ for the methane molecule. So how many are there in carbon? It's a triple CCPV-TZ, sorry. So carbon has 1s, 2s, 2p, 2s prime, 2p prime, 2s double prime, 2p double prime. So that's a triple zeta valence. Then, since it's a triple zeta, I'll have 2 sets of angular momentum, and that will become my 2D, 1F. Correct? And then I will have augmented, means one more diffuse function. I write in a different manner, just to indicate this is a diffuse function. And now we start counting. It's very easy. How many total S are there? 1, 2, 3, 4, 5. How many P's are there? 1, 2, 3, 4. So it is 5 number of S function, 4 number of P function, 2 number of D function, 1 number of F function. So you can do your calculation. 15 plus 12 plus 10 plus 7. So 27 plus 37 plus 7, so 44, just for the carbon. Do the same for hydrogen. So for hydrogen, I have 1s prime, 1s triple double prime, because it's a triple zeta for hydrogen. And then I should have, so I already did this for the hydrogen. Augmented CCPV TZ will have a 2p and a 1d, because I'll have 2 angular momentum, and that should be 2p 1d. And then I have a diffuse S function. So total number of S orbitals will be 4, 2p, 1d. So 4 plus 6 plus 5, that's 15. So if I do the methane calculation, how many will be total molecular orbitals? How many will be total atomic orbitals? 44 plus 15 into 4, 60, 104. You can see how quickly it is running up. Of course, for 5 occupied orbitals, rest of the 99 will be unoccupied orbitals. Somebody may ask the question, why do you need unoccupied orbitals? You need, because even the occupied orbitals are expanded in terms of the k number of atomic orbitals. So I need as large a k as possible. So don't forget that. My original idea of the Ruthan calculation was that a molecular orbital is expanded in terms of the atomic orbitals. Let me go back. Yes, here. So each of the molecular orbital is expanded in number of k orbitals. So even if I require my occupied orbitals, I require as large a k as possible. So let's not forget that I require large number of orbitals. So of course, in terms of number of occupied orbitals, there will be 5, and you build in number of unoccupied orbitals, which will keep on increasing. But the calculations are getting more and more refined. In terms of DFT, I must mention that many of these correlation consistent basis set that I discussed are actually used in the ab initio methods. DFT is somewhat simpler because of a very inherent fact that in DFT, the convergence of the energy with the basis set is faster than the Hartree-Fock based methods, which means wave function methods. So that is another advantage of DFT. We talked of so many advantages of DFT in terms of simplicity and so on, computational cost, but the basis set K can be also less. So what you will get in terms of, what is convergence? If I keep on increasing my basis set, just as I'm doing here, up to 104 have come, CCPV DZ, augmented CCPV DZ, augmented CCPV TZ, QZ, I'm actually increasing the number of basis set, and the energy would eventually converge. So if you look at ideally what will happen, if this is energy, this is my basis set number, then I will have some energy which is very high, somewhere in low basis set. And then it will become lower and lower, because you know the basis set, as I increase the basis set, the energy becomes lower, and eventually it will get converged. Very large basis set, the energy will not change. So that's my final energy. However, if the same number I can reach faster. So let's say I start with very similar number and I reach here much faster, the same value. Of course, this is better because the same number of basis set, a smaller number of basis set has given me the value. Here, the same thing goes very, very slow. And this is exactly what happens in DFT. And this is the Hartree-Fock or Hartree-Fock based methods, post Hartree-Fock methods. So DFT is in a way much faster, and people have realized that you actually do not require so complicated correlation consistent basis set, very often augmented, and you can devise basis set limit results with much smaller basis sets. And they are called polarized basis, polarization basis set, I should say. Polarization consistent basis set. Unlike correlation consistent, it's just called polarization consistent basis set. And those are very, very interesting bases. I will not worry about it. They are very often nomenclature as PCN n sets, and they can also be augmented with diffuse function. See, as I was telling you, the basis set, there is no end to it. But you will find, instead of CC, you will find PC basis set. It's very similar, number will be less. And many times DFT actually uses this. There is another kind of basis set. Again, I don't want to discuss. I think you have already understood the whole idea of basis set. You have an atomic orbital. Each atomic orbital is written in terms of primitive Gaussian. You have polarization function. You have diffuse functions, period. That's the most important thing. But there are several ways people have done it. One very important basis set that is in literature is called the Karlsruhe basis set. It was done, of course, in Germany, in the Karlsruhe group. The Karlsruhe group of quantum chemistry is very famous, and they have done lots of work in Karlsruhe. So this is called the Karlsruhe basis set, which are basically called. So one of the basis set is DEF2 SVP. So this is called split valence. So what is important is to understand this. Split valence with polarization only on heavy atom. Not hydrogen. So basically just star in Popel's nomenclature. You can have split valence with polarization everywhere. So then you call SVP. What is the difference in SVP and SV bracket P? Bracket P is only on heavy atom, which is carbon here. And this is with carbon as well as hydrogen. You can have DEF2 TZVP. So it is valence triple zeta with polarization. So very similar nomenclatures are there. You can also augment that to the basis functions and so on. What is the difference? Numbers are all same. The difference is the way these are constructed, the atomic orbitals. The construction of atomic orbitals in terms of primitive Gaussian makes it a difference. So these are all atom centers bases. I must end the basis of literature with a new kind of bases which are used actually for periodic solids. I will not talk much about this because this is not useful for organic chemists or even inorganic chemists with a molecular model. But those who are doing solid calculation, we use what is called the periodic basis. So plane wave basis. So actually these basis sets repeat. So there's a repeating unit in solid sets, so single crystal unit cell, it repeats. So these are called the plane wave basis set. They're used for the periodic basis. So those who are interested can read the plane wave basis set. These are not used for molecules. So what I have, of course, restricted my discussion of basis set is on basically molecular basis sets, which are the Gaussian basis sets. All of these that I talked is, of course, however, Gaussian. Gaussian with different number of atomic orbitals, different nomenclatures. They have, of course, different way of mixing, but basic philosophy is same. So Gaussian basis, these are not Gaussian. Please remember, this is not Gaussian. Okay, plane waves are not Gaussian, so forget about it. I'm not going to discuss plane wave, but I just thought I'll mention it. So for the Gaussian basis, there are, so basic idea is that as a summary, there's a plethora of basis sets. There's no end to it. And basis can become larger and larger. By split valence, double zeta, triple zeta, etc. Number of polarization functions, number of diffuse functions. And this can be numbers, like as I told you, in correlation consistent, the number of polarizations are much more. Angular momentums are not just one higher, two higher, three higher, with different numbers. And then, of course, each of these orbitals, these are atomic orbitals, each of these AOs is built by linear combination from primitive Gaussian. So eventually, entire program runs on Gaussian integrals. So you have contracted Gaussian, which is atomic orbital, and a primitive Gaussian. Let's not forget why you do this. The multi-center 2-electron integrals, I told that in the beginning of the class, but let's not forgotten, multi-center 2-electron integrals are simplified using Gaussians. So that's the main reason that we used Gaussians. I think this is in summary. There are so many basis sets. I mean, it's impossible for anybody to remember all the basis sets. It's important to remember some of the important basis sets, which is what I've discussed here. But you can always go back. The important thing is to understand how many S, how many P, how many D, how many F, how many G's are there, including polarization, valence, diffuse. How to do the calculation. Unfortunately, in the Popple's nomenclature, the appearance of 6, 3, 1, etc. confuse people. These numbers confuse people. And I think the Dunning's number, Dunning's nomenclature is somewhat better. And that is what the correlation consistent has come back to. PV, DZ, PV, TZ. So you exactly know. Here it does not, you can sometimes get lost. For example, this is double zeta actually, because there are 2 entries right at the separator. So it's a double zeta valence. 631 don't mean anything. They're only to construct those basis functions. But in terms of atomic orbital, 631 have no value. Plus plus and star stars have value. So sometimes Popple's nomenclature confuse. I have to say this because many people use this Popple's nomenclature. So you must understand. If you use correlation consistent nomenclature of PVDZ, you already know that valence has n number of zeta functions. You already know. And then you have n minus sets of angular momentum higher than the valence. For each of them, it starts from n1, n minus 1, n minus 2 up to 1. And then you can calculate. So this is somewhat easier. If you just put augmented, in addition to these, there's a diffuse functions. That's all. Diffuse valence function. Number calculation becomes very easy. In Popple's basis, actually it confuses sometimes because of this appearance of, because they actually tell you how these are constructed. Here, that is not known. How each of them are constructed is not known. How many Gaussians are there? So in a way, Popple's nomenclature gives you more information. That is, you also know how each of the atomic orbital is constructed by how many primitives. That's a good thing, but it can also be confusing. The information may also confuse. So I think keep this in your mind. And many times I just said that the polarized and diffuse function, there are no Gaussian, they're all uncontracted. There's one Gaussian, just exponent is there. The literature has a basis set in which all these values are actually detailed. But you should just know what it is. You don't have to remember exponent. Nobody will ask you to remember Gaussian exponent. That's not possible. Okay, so do not worry, periodic solid state, you use completely different basis set. I didn't discuss the Karlsruhe basis set much, but I think it's very simple. We just have a different nomenclature. Remember, the plane waves are used for periodic solids, periodic basis. All right, and some of the summary in the Gaussian basis set. Shubhajit, what I also want to do is to send you all the slides, if that helps, apart from the recording. So the slides can be sent separately for all my lectures, and then you can distribute to all the group. Okay?
Sure. Sure.
Okay. I think with this I will close, and I will take up the discussion on the functional. That's very important. We have not come back to EXE, exchange and correlation, how to handle. So that is still limited. This is because the kinetic energy brought in at orbitals, remember? And then the orbitals have to be described in terms of atomic orbital. That is how this basis set literature came, because The atomic orbitals, which are Slater, cannot be handled computationally. So Gaussians came. Remember this. So the flow has to be remembered. I think that is very important. Flow has to be understood. And then the many details are there. I didn't intend to do in that much detail the basis set, but eventually it kind of went that way. All right. So I ran out of time for this functional discussion, which I will do hopefully in 1 hour. I'll be able to finish, but maybe 1 hour 10 or 1 hour 15 minutes. So on the Tuesday at 8 o'clock. So please do not get confused with the time. Okay. All right. So if there are any questions from anybody, it's already 15 past. If not, I will stop and come back to the screen. All right. So if there are any questions, you can still ask me. Otherwise, we'll stop today's class. Okay.
I think in the chat there are many things. Let me see if there is some question. No, I think they are saying the thank you, sir. That's all.
Okay. No, I didn't see the chat. How do you see the chat in the mode?
No, it's all thank you.
Yeah, okay. Fine. No problem. So there's no question, then it is okay.
Yeah.
All right. Yeah. Okay then. Thank you very much. I hope the basis set will remain with you. It's very easy to forget.
Thank you.
basis.
Yes.
I can tell you because it's a number. Yeah. And much of the time it's just arithmetic. Huh? So it's not very difficult. Okay, all right. Thank you very much. And I will leave and we'll join on Tuesday.
Okay.
Okay. So Tuesday link you please generate and send.
Yeah, I will do it. Yeah.
Oh, thank you. Thank you. Bye. Bye.
Bye-bye.